ladies and gentlemen, alumni from EEE NTU. I'm very happy to have a chance to interact with you again. I just got a message from the chat. He was my ex-FYP students. And hello, and then probably more than one of you in there. And so please come back to NTU and let me know, and we will have a chat. So today I'm going to speak about the multi-modal sensing and intelligent systems. As Prof mentioned, now the time has come for robotics and intelligent systems. And about 15 years ago, as Wyson was chatting just now, 15 years ago, actually, it was not a good time because the job market was not there. Indeed, these intelligent sensing and intelligent system technology developed so fast, and now it's close to maturity. And if you look around and all over the world, and there are a lot of intelligent systems, most obviously to us are the autonomous vehicles. And they are in the news all the time. And for these intelligent systems, and they are intelligent because they have multiple capabilities. The first one is the sensing. They have to understand the environment. They have to understand what they see, because a human are not there. We use a computer vision, we use other sensors to understand the environment. So when we use a sensor, multiple sensors to understand the environment, actually it imposes a challenge for the technology. How to combine this sensing or sensors to make it, you take the advantage of each and overcome the shortcoming of the others. So we want to combine all these and make sure that our sensing is good in all situations, in all weathers. Because in real life, we humans are just so capable, and in any situation, we understand the situation. We can, based on that, make a judgment, make a decision, and act accordingly. So this is a motivation of why we use a multi-modal sensing. For myself, I've been doing research over 30 years now. I've been working in all these areas like diagnosis and prognosis, and robot navigation and control, intelligent transportation system, and more recently, multimodal perception. And then I do feel that this is really has a tremendous potential for applications in different fields. I try to touch the application of this capability, these sensors, and to different applications with different functionalities. Firstly, I want to acknowledge my team, which actually now grew to about 26 or 27 researchers. I'm still recruiting. And among all these 26 team members, actually quite a few of them are PhD degree holders, and majority are master degree holders. They are very capable from theory to implementation and system integration. They have all kinds of backgrounds. So we are able to manage from theory to implementation for the whole chain by ourselves. And as you can see that our systems are developed in various scenarios, in outdoor, indoor, and so forth. And then we have achieved quite a few meaningful results in the past, and then we have won some awards.
In January, NEA announced the launch of proof of concept trials of autonomous environmental services vehicles for road cleaning. These self-driving vehicles are controlled using computing units, enabling remote operations and dynamic planning.
And we have been working with industry for the past 15 to 20 years. And from there, we do see a lot of application requirements. And we basically, government, mostly from NRF, provide us funding, and we work with ST engineering. We work NEA and Continental and some other big company. I also work with some smaller company as well. And so these are the major fundings. So from these collaborations, we realize actually application out there demand some intelligent sensing. And they want to have a reliable sensing capability to upgrade their equipment, their capability from the current version to the next version. So the next version is enable it with intelligence. So how to do it? The sensing is the key. And in the past research, and then we have filed quite a few patents, mostly on these sensing and intelligent sensors. So one typical example of this industry requirement is we are working on a project on this autonomous sweeper. The problem statement is coming from this NEA. They want to enable the sweeping, the environmental service with the newest technology, the deep tech. So we have gone through this, we have done this project in the past 3 to 4 years, and actually we have achieved a lot, as you have seen the TV. And if you search the sweepers, NTU and or teleoperation NTU, you are going to find the media information. So in this project, basically the vehicle need to move in the outdoor real scenarios. They have to deal with all kinds of situations. In the good day, in the morning, in the afternoon, in the noon, the sun comes from different angles. During the foggy days, during the rainy days, and during the different situations, and even smoke. So under these different conditions, the vehicle cannot stop in the middle of the road. It has to go on by itself, and then without stopping. So it's no longer a laboratory setting. It's a real scenario. So in this case, we equip the autonomous sweeper with multiple sensors, like a LiDAR, like a camera, like a thermal camera, and then the IMU and GPS and all kinds of sensors. So when we have so many sensors looking around the environment, we need to understand how this information are fused together and how do we interpret all this information to achieve a meaningful information so that the computer can understand and follow up with decision and executions. So this one is, as I mentioned, actually, the intelligent sensors actually promote the upgrade and iteration of the intelligent perception industry. And just like environmental service, now it's being done by some foreign workers. We hire them to drive the vehicle. And then in the future, actually, it could be the people are sitting in an air conditioning environment, and then they are teleoperating the vehicle, or the vehicle is running autonomously in the outdoor. So this one will make the upgrade the whole industry sector, not just one individual machine, the whole sector. So our Singapore young people might be interested in going there, sitting in this nice environment, playing with these intelligent big toys. Actually, it's not just 1 or 2 stories. And then if you look at the market survey, and these intelligent sensors, it has a great future. And by mid of 2023, this advanced perception function will become a standard configuration of collaborative robot systems. And then these days we hear about robots, but actually single robots is basically mature. And then what we are looking into is actually when we deploy robots, we want to deploy them in large quantity. So we are going to manage a fleet of vehicles, a fleet of robots. They need to work together. So the perception of each robot or as a team of robots will become an important issue. With more perceptions from multiple vehicles, multiple sensors, actually you can enhance this intelligence tremendously. Everybody heard about this Tesla, and they have camera systems on each of their this autonomous vehicle. When they run around, they collect all the information and put into the cloud. So the cloud will provide the training and then get the information, and at the same time feedback to the individual robots, the vehicles. So basically, this is collective intelligence, and then based on multi-modal, multi-sensor, multi-robots. So there is an example, but between the Tesla's intelligent vehicles to what we have now, actually there is a great potential to upgrade your current system, okay? And the smart sensor will be able to make it happen for you. Now in these intelligent systems, basically we have a multiple layer of execution. So first one, we need to have a perception. Then we, based on the sense information, we want to interpret what is in front of us. It's a car, it's a stone, it's a cat, it's a human, it's just a fallen branch of a tree, right? And then the decision layer, based on the information, we need to make a judgment and what should we do? And without the input from the sensing, the decision layer won't be able to think, to do anything. And then once the decision is made, then the execution layer will carry the system forward to do things like moving, like picking, like assembly, whatever. And of course, from this perception layer to decision layer, and then we have various technology like sensor calibration, environmental perception, and data fusion, and so forth. Now, my team and my group actually have been working on these key technologies and enable the sensing to decision. So execution will depend on the platform. You have a machine, you have a vehicle, or you have some other things, excavators or any other things. But basically, the sensing is the first line of intelligence. And of course, here illustrate two examples. And then one is for this mobile autonomous system. The other one is for smart urban traffic control. And believe it or not, actually, this current traffic control system in Singapore was invented in 1970 and 1980s. So it was a half century ago. And we are still using the old technology, even though there's some upgrade and it's a minor thing. Over the past 40, 50 years, and then sensing, computation, and communication have developed so much, we can make this intelligent system smarter, a lot more smarter, okay? So in the following, basically we understand the potential of this sensing and multimodal sensing, and it's a first line of this intelligence. Now let's look at what can we do with the sensing and what we have done. And then from here, probably we can, hopefully we can spark some potential thinking, feedback, and application. And we have done mostly, today, I mean, we have done a lot of intelligent systems because of time constraint. I'm going to focus on mostly perception and fusion level. And then the decision will be something in following to follow this. So we are not going to focus on those. So for this intelligent sensing, which is the first thing, And we want to have a good sensing capability. The first thing is we need to have suitable sensor suit. That means that based on the application, you need to choose the right sensors, their range, their capability, and what you want to see and what results you want to achieve. And then you select a set of sensors. They have different capabilities and put them together. And then such as on top of the car, on top of these traffic signal poles, and then so in this case, and then you based on this input, and you can fuse them and get what you want. So these will actually require some integration of some sensors. These are some of the products we have developed. Like this one is a handheld sensing device, which can give you the result of detecting people and chairs and table and cars and airplane and whatever. So I'll show you what it can do later on. The other one is on board of a vehicle. So we have two sensors on the two sides of the vehicle, and then we have one unit which is in front of the driver. So this one basically is a assistive perception. So in many situations, we human beings are not able to see so many things or monitor the danger. So this system will be able to help us to monitor the front, such as in the airport, this tow truck vehicle, and then when they push, and then actually the vehicle pushing a huge aircraft, and then you hear about the accidents, collision between the aircraft. That is actually a tremendous loss to both the airline, to the passengers, to cause a lot of problems. We also have developed these tower mount perception devices. So these from handheld to on board and to the tower mount or mount on the buildings. So we have designed all these based on the requirement. Now, with all these combination of sensors, and actually we can do a lot of things. And here it shows during we need to have a capability of perceiving detection from day to night. From the days we have seen, a lot of people have seen it, use an RGB camera with some intelligence. Then we are able to detect and track many dynamic objects. But when the evening comes, then it's a challenge. Now here is in front of a Hall 7. So at night, it's completely dark, and the RGB camera cannot see anything. And then, but we combine with thermal and this LiDAR, then we achieve this result. How to interpret this result? And you can see that with the LiDAR, we are able to map the static environment. We know where are the trees, where are the road and the fence, and then we are able to detect where are the individuals, and then their locations are pinpoint in the static map. So these are all live, can do it. And now we have developed this. Oh, the previous one is based on calibration technology, which we developed. We can calibrate. When you put the sensors together, then you can calibrate this quite easily. And the baseline normally is short, okay? And here we have another set of technology, which actually is a long baseline. As you can see that we have one sensor suit here, the other sensor suit is on the other side of the building. They are actually quite far away, quite arbitrarily, and they are placed at random. So the calibration can be done almost instantly. So the result they achieve is actually each sensor can see the environment from one angle, and then the other sensor will see the environment from the other angle. We are able to put all these sensors, these point clouds, into a single frame. And then all these vehicles will have a complete 3D model of these point clouds. So this is actually can be used in multiple applications, like a digital twin for many applications. And then the methodology here actually require minimum human calibration. It's just one key, and we can do this calibration automatically. So another application is we are putting it in this overhead bridge, looking down to the highway, and then the two cameras, two sensor suits, actually looking into the highway, and then the left and right can detect the vehicle from two angles. And then we can combine this point cloud into one, and with a denser point cloud with a 3D model, actually the detection will be more reliable. Tracking will be more ensured, because occlusion happen all the time. And then when you are dealing with a vision-based system, this is one headache people are facing. So we solve that problem. And then we look into the all-weather situations, and then when we are dealing with the real situation outdoor, that's my research area. We have to deal with all kinds of situations, and this is quite foggy, and then in the evening and in the rainy days as well. So our sensor, actually, you can see that we can detect the depths. So we can create a tracking system with a bird's eye view. So we look from the top, we know that vehicle in front, where they are. We can keep track of them, even though they are occluded from time to time. Okay, and then also we can do this detection of a multiple objects. You can choose anything you like. We can detect them. Like first we choose people, and then the half a head, we can detect it with a distance from the sensor as well. You choose chairs, we detect them. And then so all these are adjustable, and then you can set the default range, and then you can even you can tune the you can choose one particular object. Once you select this, it becomes purple, and then all the readings are actually the distance from this chair. So if you want to see a crowd, whatever, and then you want to measure their relative distance, and this sensor will give you that capability. And just now I missed one. Anyway, so we can define the safe range and the danger range and anything in between. So those are arbitrarily defined by our system, by human. So here is another one, and then we can use the 2D information. We can create a 3D and project its coordinates in terms of X and Y, and keep track of the individuals or the vehicles. So this has been done. So we also have used multi-modal, multi-modality to achieve some amazing results. Like in this case, in these foggy conditions, the RGB will not be able to see. LiDAR will not be reliable. And then we are using thermal. Also, the other two, we fuse them. And here illustrate two methods. And then the first two are the fuse method. The bottom one are the single image based. All right. So on the top, actually, if you frozen any frame, you can see that we can detect all people, even though they are not visible, okay, by human eyes. We are still able to detect them. So this is the power of this multimodal sensing. And in this case, we aim into the depths as well. We use a LiDAR and then the thermal and this RGB. So we have various fusion methods, and then you can see that actually we can achieve the detection and localizations with precision. And because the LiDAR provides pretty good. And then you can see the individual sensor-based detection, and they are not reliable from time to time. But when you fuse them, actually, they are a lot more reliable than single images or single sensor. Okay. Besides that, we actually have, because the sensors are commonly used these days, and they are subject to cybersecurity threat as well. And in particular, in autonomous systems, and LiDAR and GPS are the prime sensors. And without these two, basically, autonomous mobile system are not be able to move. And that is the fact. The other two are the actuations, the steering and this speed control. And so we look at the sensor part today. We are concerned about the cyber attack. So what we have done is looking into these two sensors, like this GPS can be spoofed, and once it's being spoofed, and then the vehicle will not recognize its own real position. It will perceive it's in a fake position. So in this case, the vehicle might think it's moving on the pavement, and thus try to move to the other side. And then this actually will guide the vehicle into the pavement or the opposite oncoming vehicles. That is very dangerous. So the other sensor, the LiDAR, can be known to be attacked by using the playback. What it means is the vehicle is in this position. Actually, the LiDAR will give you the point cloud of this place. Instead, when under this cyber attack, and then the point cloud in a different position will be fed into the computer. So it will cause a confusion to the decision and or the intelligence system. Now we use this autonomous whipper to do a test. We use a GPS camera, LiDAR, and IMU and actuators. But today we are going to talk about sensor also. And then we have a look into various attack scenarios, and suddenly the attack stopped the reading of the GPS. Normal reading is like this, but it stopped the reading. Sometimes it gives you a false reading, and the most challenging one is it gives you a continuous false reading. So this one is very difficult. And for the LiDAR, and as I mentioned, it gives you a earlier recorded point cloud. And here we have developed the algorithm, and then we implement this in the real vehicle. Here it shows LiDAR is under attack, and this guy launched the attack from a remote place. And then the vehicle, this one is without the detection algorithm, so it gets confused to move into the side, the parked car, so the safety driver has to brake it. Now, when we use our detection algorithm, and we are able to detect the interferences, the hacker, and then once it activated, it can be detected and then stop the vehicle. So we have done this many times. For each scenario, we have carried out 20 times trials each time, and every time is successful. And then even for the multi-sensor attacks, that means two prime sensors, both are under attack. Then both prime sensor, the major informant, are telling you you are wrong, or telling you the wrong information, you tend to believe. It will be difficult to figure out. So in this case, it took a bit more time to identify there is an attack. Otherwise, for single one, actually, it's detected in a fraction of a second or within 2 seconds. We also, So using multi-modal data, actually we can achieve a lot more than a single one. Like in this case, and the LiDAR give us a point cloud. It's being used by autonomous driving. It's good enough for the machine. But for human, we cannot drive or teledrive based on this 3D point cloud. For teledriving, we need to use this video. But the problem with this video is it causes a lot of bandwidth problem, and then it will cause a delay. So for the high-speed and heavy-duty vehicles, this is not acceptable, and then it's very dangerous. So we fuse this tool and we generate a 3D color point cloud, which can be used by the autonomous system and can be friendly to human being. So with this mapping, actually, we can create a very large map. We call it a 3D digital twin of the environment. So it can be used by autonomous system, can be used by human beings for different situations, right? And when we use a when we do teleoperations, we use multi cameras, and then this camera will give you one video. You drive like this, it's not very friendly. We develop technology which will be able to stitch all these 3 videos in real time. Offline, we have that in our phone, right? You have a panorama, this capability to take a photo, multiple photo, it will stitch for you, but it's done offline. And here we are talking about real time and fast real time, because for this teleoperation, and we have to do it within, say, in the unit of this, in the scale of milliseconds or a dozen of milliseconds. So we have done this, and then this is a sum of this combining different sensors. So we fuse them for different applications, achieve different capabilities. And we use our own developed sensors. We can achieve this traffic monitoring. We can detect the vehicle, track the vehicle, different type, and the pedestrian, the bicycles, and all kinds of different road users. And at the same time, we have their distance, and we can create a bird-eye view for the monitoring if they wish to use it. And this one is for from the highway system. We use a LiDAR because multiple video are playing at the same time, so it's slower. Basically, in the highway, we are able to detect these vehicles from far away, about 100 meters, and then with a minimum effect due to the occlusions. So we are able to count the vehicles and calculate the speed and track the vehicles. Even in the evenings, when the RGB is not working fine, we are able to do the same thing in the evening. When the traffic is light, the vehicle is running at high speed, 90 kilometers per hour. Then we're still able to detect them, track them, and then count them as well. Okay, this is so due to time limitation, I'm going to talk about another one. This one is a teleoperation. Teleoperation is nothing new in terms of a concept and devices. There are lots of out there. But for heavy duty and fast moving vehicles, the current teleoperation system doesn't work well, in the sense that even they use only one small screen because they don't want to beam back so many videos. And yet they still have to suffer from a long delay. And a very common delay is 1 second. And for 1 second delay, that means it's between the camera capturing the real scenario to the time when the teleoperator see on the screen 1 second. That is not acceptable when we are doing the teleoperation. Now we use robotics and sensing technologies, multiple sensing technologies. We are able to do this teleoperation with comfort. Now here, what we have come up with is a teleoperation platform, and which has the motion, which is also based on the sensor. Okay, so this guy is sitting on this platform operating inside an air conditioning environment. Then he's driving a vehicle in the outdoor. So when the vehicle is moving outside, he feels the same. He feels like he's sitting in the real vehicle. The other thing is the videos is mounted on the vehicle. So when the vehicle is moving, and the vision or the video is moving as well. Now, if we don't have a moving platform, then you're sitting there motionless, but your eye is moving, the vision is moving. Then very soon you are going to have a motion sickness, okay? Because you don't feel your body is not coordinated, not synchronized. And then, so that is dangerous for driving as well. So now we have developed this system, and then motion, vision, and auditory, they work together. And then so that teleoperator can feel like he's driving in a real vehicle. Of course, here, there is one critical technology, which is the image processing and multi-sensor fusion. And then we manage all these in such a way that we cut down the bandwidth requirement. We send them back with only 190 milliseconds. Now, basically, industry or the experience tell us 250 milliseconds is the bar. If your feedback latency is smaller than 250, then you feel very much natural. You feel like sitting in the vehicle. If your latency is beyond 250 milliseconds, then it's going to be dangerous. Okay, so we achieved this, and then very successful. This video was done long ago, so now we have one big screen, and all the video are stitched together now. And with our technology, I mean, we are working on a new technology. We're able to cut down the bandwidth requirement tremendously by 13,000 times. So currently, we have 4G, we have a 5G, but 5G is not popular yet. And even 5G, their blind spot coverage is not good enough. So very often, the transmission is not doable, even in the 5G environment. And so we developed the technology, cut down the bandwidth. That is relying on this multi-modal sensing technology. And then with that, we can cut down the bandwidth, the data transmission rate by this much. So we can operate in the 3G. So that is a wonderful reliability. Oh, okay. I guess after this video, I have to stop due to the time limitation.
Fully autonomous transportation will be a part of our daily lives in the future. Today, human intervention is still needed in the teleoperation of autonomous vehicles. Current teleoperations on 4G do not receive sufficient communication bandwidth for real-time sensor and video data transmission, causing substantial latency in teleoperation and haptic feedback. Without real-time haptic feedback, teleoperators using these systems are prone to motion sickness. As part of the 5G at Sentosa program, the National Environment Agency and Nanyang Technological University are trialing high-fidelity teleoperated autonomous vehicles connected on Singtel 5G. The developed system provides 180-degree frontal image surrounding the driver, and the first in the world to simulate vehicle movements, acceleration, and steering wheel stiffness in real time as haptic feedback to the teleoperator.
We can use this teleoperation to control a driverless vehicle, such as a sweeper, in a remote location. And here the teleoperator is in NTU and the sweeper is in Sentosa. So in this teleoperation, there is a requirement of transmitting large amount of data from Sentosa to NTU.
With 5G, videos with maximum achievable image quality, haptic feedback information, and control signals can be transmitted back to NTU in real time, allowing the teleoperator to respond immediately.
So we partner with GovTech and Singtel to carry out this trial at 5G at Sentosa. And so far, the result has been very successful. So due to the time limit, let me stop this one. And so I move on. So basically, our multimodal sensings have achieved, and they were carried out in such objective, achieve such features. So they are modularized and robust against all weathers. And then we are able to continuously track the objects. And then we have a long baseline collaboration. So when the sensors are putting arbitrary distance, and then we can do this calibration easily. We can work with this 5G and broadband and long-range Wi-Fi and achieve the desired results. Okay, so this is something we have. I guess I don't have to say too much, and then you can imagine basically wherever you require intelligent system, and the sensing is the first capability you want to have, and that is the first line of intelligence. Okay, so due to time limits, and then let me stop here, and I welcome questions and discussion and suggestions.